Good morning, Dan Guerra here from Authentic Biochemistry Studios in the Inland Pacific Northwest. Today is the 19th day of June 2021. We're doing this video lecture because we're trying to set up the final stages, the last great fourth movement of our long arc of discussion of aging, morbidity, and mortality in humans. So let's get started with the show. I'm labeling this cancer and aging immunosenescence, as you can see. And the reason I'm doing that is because we're going to try to be talking about one of the major, if not the major cause of death of most humans as they age, a disease that is associated with mortality and high levels of morbidity, where that morbidity level increases logarithmically as one ages. And the mortality, obviously, since it's linked to cancer, is one that more often than not is associated with older people rather than younger people. So we can ask the question, and we'll try to answer it as well, whether or not cancer causes or is associated with the aging process, the rate of the process, and the quality of the process, or if indeed the aging itself is emitting or enabling oncogenic events, so that tumors grow and that people that become more elderly generate cancers because of the aging process. So those are two different ways of looking at it. There's a third way of looking at it. And by that, I don't mean they interact, because it's obvious they interact. Third way of looking at it, and that would be some component of an etiologic agent that could intervene sometime during the lifespan. And maybe that agent, either internal or external, is the more close correlation to how cancer, morbidity, and mortality are linked. We will cover all three of those possibilities if I remind myself. So I'm going to hide this for now and move on. Paper that came out in 2013 is an annual review. I like to use annual reviews before I get into the deep peer review literature. What does this tell us? Aging is marked by progressive decline in the function of multiple cells and tissues. In organisms with renewable tissues, like in humans, aging is also marked by an increase in hyperplasias, most serious of which, of course, are cancer. You can ask the question, why does aging occur? So we've talked about this in maybe the ancient past in this lecture arc, but let's go back and revisit it. Evolutionary theory holds that aging is a consequence of the declining force of natural selection with age. Extrinsic hazards, and those we are well aware of, and I've talked about this in the past, accidents, predation, infection, starvation, limit the lifespan of most species, and thereby depleting natural populations of the older individuals, so that the median and the mean of a given population of mammals in the wild is going to center around the middle age of that group, and you're going to have far fewer older people. You're going to probably also have fewer very young people, because in a natural population, because of predation and disease and malnutrition, many animals that live in the wild that are not human, there's a lot of infant mortality. And in humans, of course, there was too in the past. Now, there are generally few older survivors on which natural selection would even act. So if natural selection is a phenomenon of biological and environmental systems, then that phenomena has serious mechanisms associated with it. And the mechanisms would most likely be apprehended more toward the earlier age groups, because as you age, there's fewer people. So those mechanisms, one could hypothesize, would be less stringently available or active to a smaller population, because it's a mechanism that is emblematic and therefore inherent in the individual and the environment. Okay, so It's an argument. It doesn't say that this is the best theory. It's a good argument, I think, that at least heeds further discussion. And we'll do that. So that's one of the ideas. Generally, few older survivors on which natural selection would act to eliminate certain alleles, that is, one copy of a gene, or the gene, or both copies of the gene, or if it's a single gene, just that one, that would have late acting deleterious effects. For one thing, I've mentioned this in the past too, when you get older, you're out of the breeding population often, or at least you're greatly decreased in it. Women's breeding age usually ends at about 45, stops ovulating, and there are a lot of inborn errors of metabolism that can occur if birth occurs after, say, age 50 with a biological mother. And with men, sperm count drops, and there are a few discussions that men aging can also introduce mutations into their haplogenome, and that's also possible. Much less so, it appears, than with the female egg than with the male sperm. But at any rate, male population probably has a longer breeding longevity than the female, and it has to do with just reproductive capacity. But obviously, as one gets older, the opportunity to do breeding, to be actively reproducing, is going to diminish in both sexes. And certainly that has been the natural way that humans have procured their reproductive capacity. So this is especially true then for genes that confer early life benefits. So you're not going to have selection pressure on genes that are normally necessary for early development, still functioning as a selection pressure as one ages. That is, and this is a way of summarizing it, natural selection can't eliminate genes that promote early life survival, but incongruously also promote late life debility. And I've mentioned this theory before. It's called antagonistic pleiotropy. Just so you have it once again. Now let's jump up to a paper published just last year in a journal called Nutrients. Take a look at what this paper says about aging. Aging is the highest risk factor for the majority of chronic disease. So a growing number of people are living longer with impaired health and morbidity. Increased aim in the health industry to improve the health and quality of life of that aging population, because people are older and they want to maintain their health. They're living longer. So we have to look at the neuroimmune system. And the neuroimmune system, of course, is impacted by age-associated changes that result in pathophysiological responses to all the major systems: endocrine, nervous, digestive, cardiovascular, and musculoskeletal systems. Both innate and the adaptive immune mechanisms are dysregulated with aging. We've talked a lot about this in the last several months, with a pronounced leukocyte inflammatory response. Inflammaging describes chronic condition of elevated pro-inflammatory mediators, including the interleukin-6 and TNF-alpha, tumor necrosis factor alpha. And of course, one more very potent pro-inflammatory cytokine, IL-1 and IL-1 beta. So immunosenescence, which we've talked about, marks an increased susceptibility to infection from external etiologic agents like bacteria, fungi, parasites, and yes, virus, and a more frequent reactivation of latent viruses, which could be held in the genome. Think about herpes. There is also a decay in the aging for vaccine efficacy, particularly in the advanced elderly. And there's also a very important component of the morbidity associated with this process, chronic autoimmune activation. And that occurs primarily through the T memory cell lineages, which we will talk again about, but which hopefully you remember from previous lectures. So at this point, we could say that autoimmunity in cancer along with neurodegeneration, have become common morbidities. Now, all three of those disorders, having an autoimmune disease, having at least prodromal and early stages of cancer, and indeed even neurodegeneration, do not outright commit to mortality. So these can be termed as chronic diseases of the aging, and they can last a long time before they ultimately can be associated with actual death, right? So they become chronic only in the later stages. All right. So we talked about aging phenotypes. Most prominent of the aging phenotype is degeneration. Generation gives rise to a well-recognized pathology. And in muscle, for example, it's sarcopenia. In endothelial cells, it's atherosclerosis and heart failure. You also get in the bone osteoporosis. You get macular degeneration, pulmonary insufficiencies. Renal failure is common. Classical neurodegeneration, including the prominent neurodegenerative diseases like AD and PD. Degeneration of one or more tissues is extremely common as you age, and it's more prominent age-related phenotype than any other age-related phenotype. So let's talk about the innate immune system changes during aging. Monocytes, which represent about 5 to 10% of all the blood leukocytes, are classed into three important subtypes. Classical monocytes express the surface markers CD14, and we say plus plus, that means high level of expression, but are negative for CD16. You also have non-classical monocytes, which express CD14 at 1 level of magnitude and CD16 at double the magnitude. And then you have the intermediates, CD14 plus plus, CD16 plus, etc. All this is at the monocyte innate immune cell discussion. So during aging, the number of non-classical CD14 positive, CD16 positive monocytes actually increases, implicating a shift to this senescent pro-inflammatory phenotype, which is linked in those cells to a short telomere length because of a decrease in the expression of telomerase, the enzyme which maintains telomere length. Macrophages, which are also in this lineage, are classified into the pro-inflammatory M1 and the more immunoregulatory or non-inflammatory M2. During aging, a shift from the M1 phenotype has been well documented. So that is to an immunoregulatory or non-pro-inflammatory M2 macrophage as a major population found in circulation. Both processes have been suggested as contributing to inflammation due to increased basal cytokine production. Increasing the M1 to M2 imbalance might be an important driver, actually, of age-related morbidity, such as atherosclerotic plaques, which is linked to foam cell formation, which, remember, is associated with oxysterol content in macrophages that occur within the endothelium, which can induce then atherosclerosis, which is a major morbidity in elderly. So in the neutrophil and monocyte macrophage, receptor expression and intracellular signal transduction are altered, as we have noted over the past lectures. That leads to a diminished pathogen recognition, defective activation, particularly of T cells and B cells, decreased phagocytosis, going back to the innate immune cell lineages, and an abnormal chemotaxis because of chemokine insufficiency or inappropriate signaling. Natural killer cells are innate lymphoid-like cells, and they represent about 15% of the peripheral blood mononucleocytes or lymphocytes, right? While several NK cell subsets can be, of course, distinguished because of cell surface markers and transcription factors and certain pathway designates. A major characteristic of those cells is the expression of this protein CD56. While CD56 bright, which means very dominant expression, are immature cells providing regulatory functions, mature CD56 dim, CD16 positive natural killer cells produce high levels of the pro-inflammatory interferon gamma cytokine. So the progressive decrease of CD56 bright reduces the amount of cells with mainly immunoregulatory functions, while highly differentiated CD56 dim cells then accumulate. So since the natural killer cytotoxicity and cytokine production depends strongly on a balance between activating and inhibitory signals, those processes I just mentioned result in dysregulated cytokine production and a reduced per cell cytotoxicity in the aging phenotype. So this leads us to tumorigenesis and aging. So among the cellular organisms with renewable, that is, of course, repairable tissues. Repairable can mean everything from allowing for new cell division, or for going through autophagy, or for allowing for apoptosis, but then some kind of new tissue production because of mitosis. Right? All of that entails another feature, and we can call it a gain of function change that allows cells to proliferate inappropriately. And of course, that's the first stage of hyperplasia, right? Excessive tissue growth. So through genomic instability, which is another paradigm of aging cells, those changes allow cells to acquire phenotypes that increase their ability to proliferate, migrate, and colonize otherwise ectopic sites, to survive hostile tissue environments, and to evade many of the aspects of the immune system. Okay? All of this becomes a phenotype which is emblematic of ultimately terminal-based cancers. Okay? Remember, it's an aging population, so when they get a cancer, they're less likely to be able to fight it because the immune system is already starting to go into its own immunosenescence. And at the same time, the ability to generate hyperplasia is increasing because of this alteration in the innate immune cells and the possibility of autoimmune responses. All right, so let's go through a lot of more of this detail here. I'm going to move the image out of the way for a second. While the total number of T cells remains constant throughout life, there are going to be considerable changes in the percentage of subpopulations of many of, for example, the T lymphocytes. And these are the ones we're keying in on now. These are very critical to understand aging. So number of CD8 positive cells tend to increase, while CD4 positives decrease. And of course, that's going to alter the ratio. Everything is about ratios in biology. Everything's about ratios in anything that's an event and possesses an event ontology, which is every phenomena. So living and aging and morbidity and dying do not fall away from that paradigm. The phenomenon itself is part of the immune risk profile, or the IRP, and that indicates a condition of immunosuppression, typically only in certain tissues, or at least heightened in certain tissues. Within both populations, aging is accompanied by a reduction in the T cell population, with naive phenotype, which of course expresses the surface markers CD45RA and CD28, while more differentiated T cells accumulate. Less naive, more differentiated or mature, okay, T cells over time. Naive T cells actually represent a pool of antigen inexperienced cells that, of course, would ensure very robust immune responses against any kind of newly encountered etiologic agent that is acting as a pathogen. So that means the reduction of naive T cells reduces T cell receptor repertoire, because remember that's based on recombination, the RAG1, RAG2 system, which decreases as T cells age. And that's mainly as a result of the thymic involution, a process of basically the thymus losing its potency in its place in high-level activity for lymphocytic generation. And that process of cellular differentiation also tanks because of thymic involution. And all that's driven by chronic antigen stimulation and further inflammation. Okay? So you have a lot of antigen stimulation because there's a lot of errant antigen recognition, because pattern recognition starts to fail as the cells age, because this is protein based. And with that, you get a lot of local inflammatory sites, right? So all over the body. In particular, one that has been well described is the human cytomegalovirus infection, which accelerates changes in both naive CD4 positive T cells composition and the accumulation of the cytomegalovirus specific CD8 positive, CD28 negative T lymphocytes. So anytime after the age of 65, now of course this is a median discussion here, so it depends on your phenotype. But after the age of 65, generally speaking, there is a shift to senescence and the accumulation of these highly differentiated CD28 negative T lymphocytes. And that phenomena itself occur more strongly in CD8 positive cells. And that, of course, would lead to a defective antigen-induced proliferation because of the CD8 positive T cells' interaction with MHC class 2. So senescent T cells undergo replicative senescence because they have shortened telomeres, first full stop, and they have a reduced proliferative capacity, just described here. And thus these lineages are strong producers of non-regulated pro-inflammatory cytokine secretion, thus aggravating further inflammation. Okay? So this is a tumbling process, a snowball rolling down the hill, right? So inflammaging describes then a persistent, non-resolving, the resolution will be death, ultimately, low-grade inflammatory response during aging that fails to move to an anti-inflammatory or regulated status, or even just flat-out repair of tissue injury or repair of DNA. Instead, what you get is a progressive, and it seems to be strong, progressive phenomena, and it's strongly related to cellular immunosenescence, which makes a great deal of sense because your surveillance capacity decreases, and the overshooting of marks because of the T cell population differentiation will only enhance an errant immune response. Right? So, inflammaging promotes aging and morbidity. That mechanism promotes aging and morbidity with increased levels of the pro-inflammatory interleukin 6 and TNF alpha in the elderly, being associated then, of course, the readout of that is higher levels of disability and ultimately mortality. Both of those cytokines are elevated in a very common disease in the Western world, type 2 diabetes, which of course is directly linked to obesity. Along with that, you get elevated cytokines from cardiovascular disease, also associated with obesity, and neurodegenerative disease and cancer, which are sometimes yes, sometimes no, associated with obesity. So the differential regulation of the non-inflammatory interleukin 10 with TNF alpha the regulation of those two opposing cytokines can be essential in predicting the progression of inflammation. So that means a great deal rests on that war between the two different cytokine populations, pro-inflammatory versus anti-inflammatory. Okay? Very important to understand that. So again, cellular senescence, physiological process. Of course, it's going to have genetic determinants, and they're going to be external modifiers, including stress, the external stresses, for example, also stress of nutrition or malnutrition, I should say, sulfate reprogramming. This has to do with alterations in gene expression, which could be a result of a mutation picked up because of reactive oxygen. And anyways, that sulfate reprogramming would include the two major discussions we've had, autophagy and apoptosis. So human aging is, of course, a lifelong teleological process. Teleological because it has a goal, and the goal ultimately is the death of the organism. So all this includes specifics of cellular senescence plus an underdefined terminus that tracks chronological longevity and occurs in all the different systems, such as digestive and endocrine, etc. And as I'm saying here, it also includes musculature, all the solid organ activity, the peripheral nervous system, and of course, the central nervous system. Aging then is at the organismal level, and it is inevitable from all the mechanisms I've been describing to you. Unfortunately, even though it's inevitable and it is at the organism level, it also increases the potential for morbidity with or without definable etiological agency, and the end absolutely is always death of the organism, the individual. So this is in contrast to senescence. The aging is separate from senescence because senescence is variable and can feedback inhibit. So tissue specific is both plastic and elastic. Okay, this tissue specificity that is of senescence is plastic and elastic, and that's all relative to short but stochastic or random changes and random progress that presents with intervals of remission and progression without a necessary uniformity of morbidity being established, or any kind of coordinated and coincidental demise or death. At the end of human life, the senescence of every tissue lineage can be rate and stage specifically independent, yet ultimately uniformly unrecoverable after a certain sufficient time after death. Both integumental, that's skin, and internal microbiota can survive post-physiological death, and of course that depends on the aerobic environment. Age-related changes in the immune system, such as thymic involution, which we've mentioned, which means a decrease in thymic output, lymphatic zonation, so where T cells and B cells are tested against self-antigen, circulation of those lymphocytes, chronic inflammation resulting from a lack of adherence to strict reduction in autoimmune responses to naturally occurring epitopes, I might add. So that's chronic inflammation, infection, which of course is errant and insidious, and of course autoimmunity, which can be the result of a combination of a couple of those factors. And that will all generally follow a course of decline in the number of naive T cells, and I just mentioned that's because there you have a more robust TCR activity, and modification of the functional activity that occurs of individual and composite immune cell populations. A particular interest is the subset of the CD4 positive cells called the Tregs. they actually maintain or hold down the fort of the immunological self-tolerance and homeostasis, still fighting infection. Human Tregs represent 5 to 10% of this total CD4 positive pool. Human CD4 positive Tregs can be divided into two key populations. Of course, we've mentioned these in the past. There are TTregs, which are thymus-derived, and then there are peripheral Tregs, which of course arise from the population in the periphery, usually from changes in the expression of transcription factors in those cell lineages. Okay, let's see if we can bring me back here. So Treg subsets are differentiated via membrane, cytoplasmic, and nuclear location. Okay. Most common is that transcription factor known as FOXP3, which is named after Forkhead FOX3 from Drosophila Molecular Genetics. Thank you, Thomas Hunt Morgan. Whose product is the polypeptide named scurfin, which of course regulates nuclear gene expression and subsequent Treg differentiation and function. FOXP3 Tregs also constitutively express the abundant plasma membrane-associated CD25, which actually is nothing more than an interleukin-2 receptor alpha chain protein, and low levels of plasma membrane CD127, which is actually an interleukin-7 receptor alpha chain receptor for that cytokine. Okay. Other characteristic protein expression patterns share discriminating co-occurrence and variable abundance. And that gives you then the whole plenum and florid constellation of potential T cell mediated responses, even in the Treg population. Okay. And we've talked about this extensively in other lectures. I'm sure you remember. And if not, you can always go back and listen to those previous talks. So, where are we at here? What happened? Very important that we get back to this slide. It's a good summary slide. Aging then is associated with an accumulation of random epigenetic, that means alterations in gene expression that are not linked to specific mutations in the codon, epigenetic and genetic changes. And those epigenetic changes, remember, those are covalent modifications either of nucleotides, usually proximal to a promoter or within a promoter enhancer to increase gene expression, methylation, acetylation, ubiquitinylation of cytosine residues, for example. But you also, of course, have epigenetic signatures in histones, which are associated with chromatin. And you also have acetylation and methylation there on histones, particularly on lysine residues, which will give you a differential change of gene expression, depending on where those groups are found and how many of those acetate or methyl groups are found on given lysine residues within different subcellular fractions of those histones. So aging is associated with that. It's also associated with decreased progenitor cell fitness. Told you about thymic involution. An altered systemic and microenvironment. This is because of the vagaries of aging, for example, associated with membrane disruption and DNA mutation. And then linked to this always is an altered immune response, or hopefully you're beginning to understand how that functions because of all that alteration of the innate immune cell lineages and the acquired lymphoid cell lineages. So the accumulation of random epigenetic and genetic alterations will give you increased probability of an oncogenic hit where you have uncontrolled cell proliferation. And likewise, all those other major contributors can lead to promoting expansion of those colonies of now oncogenic cells. That can then give you full-blown cancer, which is, again, very common as you age. So check this out. Number of cases per 100,000. This comes from the National Cancer Institute. And you can see that breast cancer starts up after 20 years of age and goes up from, say, 10 to 20 per 100,000, all the way to maybe 50 or 60 by the time you've doubled your age to 40. This is breast cancer. But then a steady increase between 40 and 60 to now you're about 175 cases per 100,000. So that on the y-axis, you're starting to build more cases as you age. You see the association. And then by the time people top out at about 80, which is the normal age or the median age, right? Because particularly for women, it might be like 85 or closer to 85. You're up to over 250, maybe 260 or 70 cases per 100,000. So it becomes much more substantial as you age. Colon has even a steeper and a more nuanced curve. Colon cancer can occur in both men and women, of course. Breast cancer can too, but it's far more common in women. Far more common. And anyway, colon cancer is about 50-50, so nobody gets out of this one. You see that it doesn't come up until a bit later, maybe about age 30, and that's because of the digestive tract picking up mutations, right? It takes about that long to that set in, so you start getting oncogenic events. And the process is kind of slow the next 20 years, but then starts to pick up and becomes very sharply curvilinear. And between 60 and 80 can make its biggest rise from less than 100 per 100,000 people all the way to 350, even up to 400 cases per 100,000. And this is particularly talking about colon cancer. So I'm going to give you this one last slide here. I'm going to stop because I know that if I cut these lectures up into smaller segments, you're more likely to watch it to the end, because there are metrics I can look at when people watch my talks or listen to the Authentic Biochemistry podcast, the audio. And what I want to do is improve on retention time so that people actually listen to the entire Authentic Biochemistry audio podcast or watch and listen to the entire YouTube video cast, right? So I'm going to stop here, but let me finish the slide. Stress response, which is termed cellular senescence, links then multiple pathologies of aging, both the degenerative association, which would essentially be programmed cell death because of damage, and then the hyperplastic, which is the oncogenic event, right, the cell proliferation, without any control. So cellular senescence is unlikely to explain all the aging phenotypes, but it has a very strong role to play in morbidity and then ultimately mortality. Surprisingly large number of aging pathologies have been linked directly or indirectly, this is the result of that, to a senescent response or a senescence phenotype, such as immunosenescence. All right, so let's close that. I don't know why that's there. Oh, look, it's recording my... Touch the wrong button. There we go. I didn't know that it would actually start typing out what I said in real time. That's really interesting. I like that. Maybe I'll turn that on sometime. I didn't mean to do it that time. That time I just meant to get to this stage. So, all right. So we're ready to wrap this up. We've only got up to slide 11, but that's okay. You can see we've got a lot of slides to get to. This is now the main course for our final series of discussions on aging in humans and the cause of morbidity and mortality. So we've just now added back the immune response and then one of the major sources of morbidity, cancer in humans. We're going to progress in this line of discussion in the very next lecture, which I'll try to do maybe sometime again over this weekend. I'm trying to get 2 full video lectures in this weekend. Okay. So I don't think there's anything else we really need to discuss other than please do subscribe to the lecture series, please do that. And also consider donating. We're in a donation drive this summer. I'd like to get more subscribers. I'd really like to make the video series much more robust in terms of how often I deliver them. I would be willing to deliver a video lecture. I could probably do 3 a week, because as you might guess, it takes me a long time to prepare the information to put into these slides. So I think I could do 3 per week, but I am going to need to see a larger audience and more subscribers so that I know that people are actually listening. I really would like to finish off the aging discussion before the summer is over. It's only third week, not quite the third week in June. So I would say about a month more to get these video lectures all out. We should be about at the end. Then what I would like to do actually is have people who are subscribers send in questions, and then we can answer some of those questions directly on the video, online on the YouTube. I would love to be able to do that. Likewise, I'm looking forward to seeing suggestions or what my listeners would like to hear me lecture on. So by the time we finish this, by this mid to late summer, I want to finish the aging discussion and this accountability of what causes morbidity leading to mortality in humans. I think we're starting to focus on that. And ultimately, the last set of slides will be on that dialectical event ontology, which, as I said, describes the 3 pillars that are associated with, I believe, all living systems. And those are a genetic component, an environmental component, and then what I call a neuro-immuno-epigenetic interactome between all 3. And it's the immune system in particular and how it is rescripted by epigenetic changes that ultimately lead to the various aging phenotypes, including the classical morbidity phenotypes, the classical diseases you find that cause those morbidities, and then death itself. And that's ultimately how we're going to end this arc of discussion on the aging lectures. And then I'm going to take authentic biochemistry into a new discussion, and I am interested in finding out what listeners would like to have me take on. I've got lots of ideas, and I'm going to pursue those, but I would love to hear your ideas as well. And that's the truth. So this is Dr. Dan Guerra from Authentic Biochemistry Studios in the Inland Pacific Northwest on June the 19th, 2021, saying bye for now.